On the first day of July, in the high desert of northern Chile, a robotic telescope no larger than a family car swung its glass eye across a patch of sky near the constellation Sagittarius. It was not looking for anything in particular. That is the strange truth about the greatest discovery of the decade. Nobody was looking for it. The telescope belongs to a NASA-funded survey with a blunt and slightly ominous name, the Asteroid Terrestrial Impact Last Alert System, ATLAS for short. Its job is to be the planet's smoke detector for telescopes on 4 continents, sweeping the entire visible sky every night, hunting for the one rock in 10 million that might be falling toward us. Most nights it finds nothing. Most nights, nothing is exactly the correct answer. That night, the software flagged a smudge. A single faint point of light, roughly 400 million miles away, out beyond the orbit of Mars, drifting against the fixed background of stars. The automated pipeline gave it a placeholder designation, a string of characters that meant nothing to anyone, A11PL3Z. It looked, at first glance, like one more anonymous piece of solar system debris. There are more than 1 million of them cataloged. Adding another is not news. But within hours, something went wrong with the arithmetic. To understand what happened next, you have to understand what astronomers actually do when they find a moving dot. They do not photograph it and admire it. They measure exactly where it is, then wait, then measure exactly where it is again, and from those positions they solve for the shape of the path it is riding. Everything in the solar system rides a closed loop. That is not a rule of thumb. It is a consequence of gravity itself, worked out by Johannes Kepler 4 centuries ago and nailed down by Isaac Newton a lifetime later. Planets, asteroids, comets, dwarf worlds out past Neptune, the frozen wanderers that fall in from the Oort cloud once every 100,000 years. Every last one of them is bound. Every last one of them comes back. The loops can be almost perfectly circular, like Earth's. They can be long and thin and cruel, like Halley's, which climbs out past Neptune and takes 76 years to return. But they close. The sun holds on. Nothing escapes. The number that describes the shape of an orbit is called eccentricity. A perfect circle has an eccentricity of 0. Earth sits at about 0.017, which is to say Earth's orbit is a circle with a rounding error. Halley's Comet runs at about 0.97, a savagely stretched ellipse, and yet technically still, a closed loop. The dividing line is 1. At exactly 1, the path stops closing. Above 1, the path is a hyperbola, an open curve that comes in from infinity, whips around the sun once, and leaves forever. When the first orbital solution came back for A11PL3Z, the eccentricity was not 0.9. It was not 1.1, the sort of borderline value you get from a long-period comet that a passing planet has nudged just barely loose. The eccentricity came back above 6. 6. There is no gentle way to say what that number means. It means the object was not slowing down as it approached the sun in the way a captured body does. It means that even after the sun's gravity had spent months hauling on it, pulling with everything a star of that mass can pull, the object still had enormous speed left over. It means that if you erase the sun from the equation entirely, this thing was already moving at roughly 58 kilometers per second relative to our star before it ever came close. 36 miles every second. Around 130,000 miles an hour, in the empty dark, before the sun so much as touched it. Nothing born in our solar system moves like that. Nothing. The escape velocity from the sun's grip at Earth's distance is about 42 kilometers per second, and if you want to reach that speed you have to be falling from unimaginably far away, or you have to be flung by a close encounter with a giant planet, and even then the numbers do not stack up to 58 and stay there. This object was not falling from the edge of our solar system. It was passing through it. It had been traveling in a straight line through the empty space between the stars, for a length of time nobody could yet estimate, and it happened to cross our neighborhood. Within 72 hours, the Minor Planet Center, the international clearinghouse that has cataloged every small body in the solar system for over a century, made it official. The placeholder was retired. The object received a permanent name, and that name contains the entire story in 5 characters. 3I Atlas. The letter I stands for Interstellar. The number 3 means it is only the 3rd one humanity has ever caught. Only the 3rd. in all of recorded history. Think about that for a moment, because the scale of it does not land on first contact. Human beings have been watching the sky carefully and systematically and in writing for something on the order of 5,000 years.
Babylonian scribes traquaient venus en clé tablet.
Chinese court astronomers logged guest stars that we now know were supernovae. Tycho Brahe measured planetary positions to the limit of the naked eye. Galileo turned a lens on Jupiter. And in all of that time, across every civilization and every instrument, we caught our first confirmed visitor from another star in October of 2017. That was Oumuamua, a bizarre elongated sliver that tumbled through, refused to grow a tail, showed a small unexplained push in its motion, and left the neighborhood before anyone could get a decent look. The second 2I/Borisov arrived in 2019 and behaved much more politely. It was a comet, plainly and unmistakably, with a proper coma and a proper tail, and its chemistry was odd but recognizable. 2 objects, 8 years, and then on a routine Tuesday in Chile, the third. But this one was different from the moment the orbit was solved, and the differences kept multiplying for the next 13 months, and they are still multiplying now. This is not a story about a rock that flew past. This is a story about an object that got stranger the harder we looked at it, that mobilized the single largest coordinated observation campaign ever assembled for a small body, that pulled in more than a dozen NASA spacecraft scattered across 1 billion miles of solar system, that triggered a serious search for artificial radio signals, that produced findings so peculiar that a Harvard astrophysicist put his professional reputation on the line arguing they might not be natural at all, and that has now, in the summer of 2026, delivered a final round of results that have left even the most conservative researchers using the word that scientists hate to use in public. Unprecedented. Let us start with the speed, because the speed is the first thing that makes the hair stand up on the back of your neck. At discovery, 3I/Atlas was moving at roughly 137,000 miles per hour. To put that in terms you can actually feel, a commercial airliner cruises around 550. The fastest aircraft ever flown under its own power, the State Route 71 Blackbird, topped out just above 2,000. The Apollo capsules coming home from the moon hit around 25,000, and that was fast enough to turn the atmosphere into plasma. This object was doing 5.5 times the speed of a returning moon mission, and that was before it started falling toward the sun in earnest. By the time it reached its closest approach to our star, on the 29th of October 2025, at a distance of about 130 million miles, it had accelerated to roughly 153,000 miles an hour, 42 miles per second. At that speed, you could cross the continental United States, Los Angeles to New York, in about a minute. You could go from the Earth to the Moon in a little under 2 hours. It is not the fastest thing humans have ever measured, but among objects large enough to be considered a world rather than a particle, it is close to the top of the list. And here is the part that matters most. When 3I/Atlas finally leaves us behind, it will be moving at precisely the same speed it came in with. Not slightly slower, not captured, not slowed, not turned. The sun grabbed it, swung it around, and gave every bit of that borrowed energy straight back. Our entire solar system, all that mass, all that gravity, 4.5 billion years of accumulated authority over everything within a light year, was a speed bump. That is what it means to be unbound. That is what it means to be a visitor. Now, the second question, and it is the one every person asks the instant they understand the first. Where did it come from? The instinct is to reverse the trajectory, run the film backward, and point at a star. It is a reasonable instinct, and it is almost completely useless. Here is why. If you trace the incoming path of 3I/Atlas backward, it points toward a region of sky in the constellation Sagittarius, roughly in the direction of the galactic center. That sounds meaningful. It is not, because the galaxy does not stand still. Every star in the Milky Way is orbiting the galactic center, and they are all moving at different speeds along slightly different paths, the way a crowd moves through a train station. Run the clock back 100,000 years and every star was somewhere else. Run it back 100 million and the entire neighborhood has been shuffled beyond recognition. Run it back 1 billion and the concept of a home address dissolves entirely. Astronomers did try. Teams pulled data from Gaia, the European spacecraft that has measured the positions and motions of nearly 2 billion stars with a precision that would have seemed like sorcery a generation ago. And they ran the trajectory backward through simulations of the galaxy's gravitational field. They found no convincing candidate. No star whose path 3I/Atlas crossed at a time and distance that would make it a plausible birthplace. And there is a specific reason for that failure, and the reason is the most important clue in this entire story. The object is too old. That conclusion did not come from the trajectory. It came from something far more powerful, and to explain it I have to introduce you to a discipline that most people have never heard of, which reads the history of the galaxy the way a geologist reads the history of a canyon wall. Astronomers call it galactic archaeology, and the tool it uses is motion. The Milky Way is not a uniform smear of stars. It is layered like sediment. There is a thin disk, a flattened pancake where the sun lives along with the vast majority of the bright stars you can see on a clear night. Stars in the thin disk are relatively young, relatively rich in heavy elements, and they orbit the galactic center in neat, nearly circular, nearly coplanar paths. Above and below that pancake there is a second, puffier layer called the thick disk. The thick disk is old. Its stars formed billions of years earlier, back when the galaxy was still assembling itself out of colliding fragments, and those ancient collisions stirred them up, so they no longer travel in tidy circles. They bob up and down through the galactic plane like horses on a carousel, crossing the thin disk, rising above it, falling back through. And because they were born early, before generations of dying stars had time to enrich the galaxy with heavy elements, they are chemically poor. Less iron, less of everything that came later. Now measure the motion of 3I/Atlas. Not just its speed relative to the sun, but the full three-dimensional velocity relative to the local standard of rest, the average motion of all the stars in our immediate neighborhood. And what emerges is a body moving very fast relative to the local crowd, on a retrograde path inclined at about 175 degrees, which is to say it is orbiting the galaxy in nearly the opposite sense to us, and bobbing vertically through the plane in the exact signature of a thick disk resident. A team from New Zealand and Oxford, working with a Gaia-based simulator that models the trajectory of essentially every star in the Milky Way, living and dead, ran the numbers within days of the discovery and reported them at a national astronomy meeting in Durham, England. Their conclusion was that 3I/Atlas most likely originated in the thick disk, and that there was roughly a 2 in 3 chance the object was more than 7 billion years old. The Sun is 4.5 billion years old. The Earth is the same. Every rock beneath your feet, every atom of iron in your blood, every drop of water in every ocean, condensed out of the same collapsing cloud 4.5 billion years ago. This thing may have been already ancient when that cloud began to collapse. Independent analyses using the kinematic age method, which correlates velocity dispersion with age across the stellar population, put the range somewhere between 3 and 11 billion years, with the weight of the evidence toward the older end. And later, when the chemistry started coming in, the older end is exactly where the evidence went. Let me put a number on that so it lands properly. The universe itself is 13.8 billion years old. If 3I/Atlas formed 7 to 11 billion years ago, then it condensed out of a disk of gas and dust around a star that was itself burning in an era before our sun, before our Earth, before there was a single grain of the material that would eventually become you. It has been falling through the dark between the stars ever since. Through the birth and death of countless suns. Through the slow rotation of the entire galaxy, a full circuit of which takes 230 million years, meaning this object may have completed 30 or 40 laps of the Milky Way before anything with eyes existed to notice it. And then, on a Tuesday in Chile, a machine noticed it. To understand why the astronomical community reacted the way it did, you have to know about the two that came before, because 3I/Atlas did not arrive into an empty conversation. It arrived into an argument that had been running for 8 years and had never been settled. In October of 2017, the Pan-STARRS telescope on Haleakala in Hawaii caught a faint object on a hyperbolic path, and the name it received was Oumuamua, a Hawaiian word meaning roughly a scout or a messenger from the distant past. It was the first, and almost everything about it went wrong. The first problem was that it had no tail. An object arriving from interstellar space should be icy, and an icy object approaching the sun should sublimate and produce a coma. Oumuamua produced nothing. Deep imaging by the best instruments available found no dust, no gas, no coma of any kind. It looked, spectroscopically, like a bare rock. The second problem was its shape. The brightness of Oumuamua varied by roughly a factor of 10 as it tumbled. And the only straightforward way to produce that much variation is an extremely elongated body. The implied proportions were something like 5 or 10 to 1. Not a potato, a splinter. Nothing in our solar system, out of the more than 1 million objects catalogued, has proportions like that. And the third problem, the one that broke the story out of the journals and into the news, was that it accelerated. As Oumuamua left, careful astrometry showed a small excess push, away from the sun, that gravity alone could not account for. On a comet, that is routine because outgassing provides the thrust. But there was no observable outgassing. No tail, no coma, no detectable gas production, and yet something was pushing it. Explanations were proposed. Perhaps it was outgassing hydrogen or nitrogen, which are hard to detect. Perhaps it was a fragment of a nitrogen ice shell blasted off a Pluto-like world in another system. Perhaps it was an extraordinarily porous, fluffy body with so little density that sunlight alone could push it. Each explanation had defenders and each had problems, and the argument was never resolved because Oumuamua was discovered on its way out. We had weeks. Then it was gone, and it took the answer with it. It was in that vacuum that Avi Loeb published the argument that made him famous and, in some circles, notorious, that if no natural explanation fits, we have a professional obligation to consider an artificial one, and that a thin, flat, sunlight-pushed sheet of material, a light sail, would explain the acceleration without outgassing. Most of the field disagreed, sometimes sharply. But the deeper point he made was harder to dismiss, and it stuck. We let it go. We had the first physical object from another star system in the history of our species, and our telescopes were not ready, and our decision-making was too slow, and we watched it disappear with the central question unanswered. 2 years later came the correction. In August 2019, an amateur astronomer named Gennady Borisov, working from Crimea with a telescope he had built himself, found the second one. 2I/Borisov was caught on the way in, which gave astronomers over a year to study it, and what they found was almost reassuring. It was a comet, a completely recognizable comet, with a proper coma and a proper tail and a nucleus around 1 kilometer across. If you had shown its images to an astronomer without telling them the orbit, they would have filed it as an ordinary long-period visitor from the Oort cloud. But its chemistry was not ordinary. Borisov turned out to be dramatically enriched in carbon monoxide relative to water, at levels far above almost anything measured in our own comets, which implied formation in a very cold region, probably around a cool red dwarf star. It also showed traces of nickel vapor at surprisingly low temperatures, the same puzzling signature that would later appear, more strongly, on 3I/Atlas. So the score, before July 2025, stood at one object that was so anomalous it defied classification, and one object that was normal in structure but alien in composition. 2 data points, no pattern. And then the third arrived, and it managed to be both. 3I/Atlas behaves like Borisov, structurally. It has a coma, a tail, jets, outgassing, and a measurable rocket effect from that outgassing, all of it textbook cometary behavior. But it carries a list of anomalies as long as Oumuamua's, and unlike Oumuamua, it stayed long enough for us to actually investigate them. It was caught inbound, months before perihelion, which gave the world's observatories time to plan. It was bright, by far the brightest interstellar object ever observed, which meant instruments that could never have touched the first 2 could work on this one. And it passed through a solar system that, for the first time, was populated with functioning spacecraft in enough places to watch it from multiple angles simultaneously. In other words, the third one arrived at exactly the moment we became capable of studying it properly. 8 years earlier, we would have gotten a smudge and a shrug. 8 years earlier, that is precisely what we got. There is one more thing worth understanding before we go further, and it concerns why these objects exist in the first place, because the answer is a violent one. When a planetary system forms, it does not form calmly. A collapsing cloud of gas and dust flattens into a disk, and within that disk, solid material begins sticking together, first into grains, then pebbles, then boulders, then bodies large enough to have their own gravity. In the outer regions, where it is cold enough for water and carbon dioxide and methane to freeze, Those bodies incorporate enormous quantities of ice. Some of them grow into the cores of giant planets. Most of them do not. Most of them remain as leftovers, trillions of icy bodies scattered through the outer disk. And then the giant planets start moving. Newly formed gas giants do not stay where they were born. They migrate, exchanging orbital energy with the debris around them, and the process is chaotic. Every close encounter between a giant planet and a small icy body is a gravitational slingshot. Some of those slingshots throw the small body inward. Some throw it into the star. And a very large fraction throw it outward, hard enough to exceed the escape velocity of the entire system. Our own solar system did this. Models of early solar system evolution suggest that Jupiter, Saturn, Uranus, and Neptune, during their migration, ejected an enormous quantity of icy planetesimals into interstellar space. Some estimates put the total at many Earth masses of material. Those objects are out there right now, in the dark between the stars, and every star that has ever formed a planetary system has contributed its own share. So the galaxy is filled with debris. Not densely in absolute terms. Interstellar space is unimaginably empty. But over billions of years, across hundreds of billions of stars, the total inventory is staggering, and every one of those objects is a sealed sample of the disk that produced it, preserved at temperatures barely above absolute zero, chemically frozen at the moment of ejection. That is what makes an interstellar object so valuable, and it is worth stating carefully. When you look at a comet from our own Oort cloud, you are looking at pristine material from the birth of the solar system, and that is genuinely precious. But it is our material. When you look at an interstellar object, you are looking at pristine material from the birth of a system that is not ours, frozen at whatever moment it was thrown out, and it has been sitting in a deep freeze more effective than any laboratory on Earth ever since. It is a time capsule launched by a planetary system's own violence, addressed to nobody, and opened by accident. The first thing astronomers did, once they understood what they had, was go looking for it in the past. This is one of the quiet superpowers of modern astronomy, and almost nobody outside the field appreciates it. The sky is photographed constantly by dozens of automated surveys, and every one of those images is archived. Which means that when you discover something today, you can go back through terabytes of pictures taken before you knew it existed, look at the precise spot where your object should have been on any given night, and stack the images together until a signal too faint to see in any single frame crawls out of the noise. They found it. Repeatedly. The 3 Atlas telescopes themselves had it in their archives going back to the 14th of June, more than 2 weeks before the discovery. The Zwicky Transient Facility at Palomar Observatory in San Diego County had it too. And then somebody had a better idea and went to a spacecraft that has no business finding comets at all. TESS, the Transiting Exoplanet Survey Satellite, is a NASA mission designed to stare at large swaths of sky continuously, looking for the microscopic dimming that happens when a planet crosses in front of its star. It is a planet hunter, but it has an enormous field of view and it never blinks. And it turned out that TESS had been watching the relevant patch of sky almost continuously from the 7th of May to the 2nd of June 2025. 2 full months before anyone knew 3I/Atlas existed. Researchers applied a technique called shift stacking, in which you align hundreds of individual exposures not on the stars but on the predicted motion of your target, so that the stars smear into streaks and your faint moving object accumulates into a point. And there it was, dim and unmistakable. That recovery mattered for a reason that goes beyond bragging rights. The brightness measured in those pre-discovery frames, when combined with later Hubble measurements of the nucleus, suggested something unexpected. It suggested that 3I/Atlas may already have been active out at around 6 astronomical units from the Sun, 6 times the Earth-Sun distance. Out past Jupiter's orbit. That is not where comets wake up. The standard picture of a comet is straightforward, and it has been well tested on hundreds of objects. A comet is a lump of ice, dust, and frozen gas. Out in the cold, it is inert, a dead rock. As it falls toward the sun and warms, the ices begin to sublimate, turning directly from solid to gas without ever becoming liquid, and that escaping gas drags dust with it, creating the glowing cloud we call a coma and the tail that streams away from the sun on the solar wind. Water ice, which makes up the bulk of a typical comet, does not sublimate appreciably until you get inside about 3 astronomical units. That distance even has a name. Astronomers call it the snow line. Inside it, water ice turns to vapor. Outside it, water stays frozen. 3I/Atlas appeared to be doing something at twice that distance, in a place where water ice is as inert as granite, which meant that whatever was driving its activity was not water. It was something far more volatile, something that sublimates in the deep cold. And this, it would turn out, was the first thread in a chemical mystery that has still not been fully unraveled. Before we pull that thread, we need to confront a much simpler question that turned out to be surprisingly hard to answer. How big is it? You would think this would be easy. Point the Hubble Space Telescope at it, measure how bright it is, do the arithmetic. But there is a trap, and the trap is the coma. Once a comet becomes active, it wraps itself in a glowing shroud of gas and dust that can be hundreds of thousands of miles across, and that shroud is far brighter than the solid body inside it. You are not looking at the nucleus. You are looking at the fog around the nucleus. Trying to measure the rock is like trying to measure a lighthouse by photographing the beam. Hubble did the best that could be done. Observations in the summer of 2025 modeled the coma's brightness profile and subtracted it, and what came out was not a number but a range. The nucleus of 3I/Atlas is not less than about 1,400 feet across, and not more than about 3.5 miles. That range spans more than an order of magnitude, and both ends of it are interesting for different reasons. At the small end, 1,400 feet, you have an object roughly the size of the Empire State Building laid on its side, or a large city block. Modest, unremarkable. At the large end, 3.5 miles, you have something the size of Manhattan, and that is where the trouble starts. Here is the problem, and it is a genuine, unresolved problem in the field that has nothing to do with aliens. We can estimate, roughly, how much rocky and icy material a typical planetary system flings out into interstellar space during its chaotic youth. Giant planets forming and migrating act like gravitational slingshots, and they eject an enormous quantity of leftover debris. Multiply that by the number of stars in the galaxy, spread it through the volume of the Milky Way, and you get an estimated density of interstellar objects. From that density, and from the volume of sky our surveys can search, you can predict how often we should catch one. And when you run that calculation for objects at the large end of the 3I/Atlas size range, the numbers come out wrong. We should not be finding kilometer-scale interstellar bodies this often. There should not be enough of them. Either we have been extraordinarily lucky 3 times in 8 years, which is possible but uncomfortable, or our models of how much material planetary systems eject are significantly underestimating the truth, or there is a population of large interstellar bodies out there that we do not understand the origin of. Some researchers argue this tension is real and important. Others point out that our statistics are based on a sample of 3, which is not a sample, it is an anecdote. Both positions are defensible. But it is worth sitting with the fact that the very existence of this object, at this size, is already mildly at odds with our theories, before we have looked at a single one of its actual properties. And then we looked at its properties. What happened next was, by a wide margin, the most ambitious observation campaign ever mounted for a small body in the solar system, and it happened under a brutal constraint. From the moment its orbit was solved, scientists realized they had a scheduling nightmare. The geometry was cruel. As 3I/Atlas approached the Sun, it was moving toward the far side of it, from Earth's point of view. Its closest approach to our star, in late October 2025, would happen almost directly behind the Sun, which meant that during the single most scientifically valuable period of the entire encounter, the period when solar heating would be cooking the object hardest and driving out the deepest, most tightly held material, Earth-based telescopes would be completely blind. You cannot point a telescope at the Sun. You would destroy it. So NASA did something unusual. In August of 2025, the agency convened a coordinated planning session and brought together teams from more than 20 different missions. Not a mission designed for this. A fleet improvised out of whatever happened to already be in space. Consider for a moment what that actually meant. These are spacecraft with their own missions, their own funding lines, their own carefully negotiated observation schedules built years in advance. Asking them to interrupt all of that and swing their instruments toward a faint moving target is not a small favor. But the argument was unanswerable. This object will never come back. Whatever you fail to observe is lost permanently, not for a year, not for a century, but for the remainder of the existence of the human species. They said yes. The Hubble Space Telescope, in Earth orbit since 1990, delivered the sharpest images anyone would get, resolving structure in the inner coma that no ground telescope could touch. The James Webb Space Telescope, parked 1 million miles out at the second Lagrange point, brought the infrared spectroscopy that would ultimately break the story wide open. SphereX, NASA's newest all-sky infrared surveyor, added its own spectral fingerprints. TESS, the planet hunter, watched for changes in brightness that might reveal how fast the nucleus was spinning. And then the campaign left Earth entirely. At Mars, on the 3rd of October 2025, 3I/Atlas made a comparatively close pass, and Mars happens to be the most heavily instrumented planet in the solar system besides our own. The Mars Reconnaissance Orbiter turned its HiRISE camera, an instrument built to photograph individual boulders on the Martian surface from 200 miles up, and pointed it at empty space instead. MAVEN, an orbiter designed to study how Mars lost its atmosphere, used its ultraviolet spectrograph to image the enormous cloud of hydrogen atoms surrounding the comet, a halo produced as sunlight breaks apart escaping water molecules. Perseverance, sitting in Jezero crater with its cameras, looked up. European spacecraft joined in. It is worth pausing on what those Mars images actually looked like, because they became a small controversy of their own. When NASA released the HiRISE frames, a certain amount of public disappointment followed. People expected a photograph. What they got was a fuzzy blob, a soft smear of light against a dark field, the sort of image that would be rejected by any picture editor on Earth. The disappointment was understandable, and it was completely misplaced. HiRISE is an instrument designed to photograph the ground from 200 miles up. Its optics, its focus, its exposure logic, its entire design philosophy assumes a bright, close, stationary surface. It was being asked to image a faint, fast-moving object tens of millions of miles away, in a wavelength regime and a lighting condition it was never built for. At that distance, its finest resolution worked out to something on the order of 30 kilometers per pixel. The nucleus, at most a few kilometers across, could never be more than a fraction of a single pixel no matter how perfect the pointing. But the image was never about looking pretty. It was about photometry. The amount of sunlight reflected from the brightest pixel places a hard constraint on the surface area of the nucleus, given an assumed reflectivity, and that constraint fed directly into the size estimates. A blurry blob with a precisely measured brightness is worth more, scientifically, than a beautiful picture with no calibration. And the point was proved a few weeks later, when the object emerged from behind the Sun and ground telescopes, now properly positioned, produced far sharper views than any Mars orbiter could manage. Farther out, the Lucy spacecraft, en route to the Trojan asteroids that share Jupiter's orbit, spotted the comet from about 240 million miles away. The Psyche mission, headed for a metal asteroid, took its own look. Europe's JUICE spacecraft, on its long cruise to the icy moons of Jupiter, captured images and data in early November. Punch, a constellation of small NASA satellites designed to study the solar wind, caught the comet's tail as a short streak of light in its wide-field views. And Juno, in orbit around Jupiter, waited for the encounter that would come in March. More than a dozen NASA missions in total. Dozens of spacecraft when you count international partners. From Earth orbit to Mars to the asteroid belt to Jupiter, an entire distributed observatory spanning 500 million miles, all of it staring at one faint smudge of ice. Nothing like it had ever been assembled. Not for a comet. Not for anything. And here is the reason it was worth the trouble, the reason that goes beyond scientific curiosity into something closer to philosophy. Every telescope on Earth and in space, no matter how powerful, is fundamentally a device for looking at light that has traveled to us. We can measure the atmospheres of planets orbiting other stars, and that is a genuine miracle of engineering, but we are doing it by watching starlight filter through a gas layer trillions of miles away and reading the shadows of missing wavelengths. We infer. We reconstruct. We build models. 3I/Atlas was a physical piece of another solar system, delivered to our doorstep. Not a spectrum. Not an inference. actual matter, actual atoms that condensed out of a disk of gas and dust around a star that is not our star, at a time possibly billions of years before our star existed, and that came close enough for us to point instruments at directly and read its composition line by line. Humanity has never held a sample of another planetary system. We have meteorites from Mars, from the Moon, from the asteroid belt, and every one of them formed from the same original cloud that made the Earth. They are siblings. This was the first stranger. And when the fleet finished its work and the data came back, the stranger turned out to be far stranger than anyone had prepared for. The first shock arrived early, and it arrived in a form so unexpected that several teams initially assumed they had made an error. Nickel. Metals do not evaporate in the cold. That statement is so obvious it feels insulting to say out loud, and it is also one of the most reliable facts in physical chemistry. To turn solid nickel into nickel vapor, you need temperatures in the range of thousands of degrees. This is why iron and nickel form the cores of planets rather than their atmospheres. In the deep freeze of the outer solar system, where sunlight is a thin memory and surface temperatures hover barely above the temperature of empty space, metal is inert. It sits there, forever. And yet, using the Very Large Telescope in Chile and its high-resolution spectrographs, astronomers detected the glowing signature of atomic nickel vapor in the gas surrounding 3I/Atlas while the object was still enormously far from the Sun, in a region where the temperature was hundreds of degrees too cold for metal to sublimate by any conventional process. There is a forest of nickel emission lines in those spectra. Not a single ambiguous feature that might be noise. A whole comb of them at precisely the wavelengths atomic nickel is required to emit at unmistakable. And then came the second half of the anomaly, and it is the half that made everyone sit up. There was almost no iron. In the natural universe, iron and nickel travel together. They are forged in the same stellar furnaces, in the final desperate moments before a massive star collapses. They condense together in protoplanetary disks. They are found together in essentially every meteorite ever recovered on Earth, in a ratio that varies within a fairly narrow band. Iron is roughly 18 times more abundant than nickel in the cosmos as a whole. If you find nickel vapor around a comet, you should find iron vapor with it in something resembling that proportion. 3I/Atlas was releasing nickel with strikingly little iron alongside it. Now, let us be careful here because this is exactly the point where popular coverage tends to leap off a cliff, and the actual science is more interesting than the leap. Astronomers had, in fact, seen something like this before. In 2021, a systematic study of solar system comets found faint traces of nickel vapor in the Comet of comets far from the Sun, including in 2I/Borisov, the second interstellar object. The favored explanation is not that solid metal is boiling. It is that the nickel is not arriving as metal at all. It is bound up in fragile molecules, most likely organometallic compounds such as nickel tetracarbonyl, in which a nickel atom is caged by 4 carbon monoxide molecules. Those compounds are delicate. They break apart at low temperatures, releasing free nickel atoms which then glow in sunlight. It is a real chemical pathway. It is known on Earth in industrial metallurgy. So the nickel is explicable. Probably. What is much harder to explain is the ratio. Even the organometallic pathway does not obviously predict nickel almost entirely divorced from iron, and no laboratory or theoretical model published so far reproduces the observed proportion cleanly. The honest summary, and it is the summary most researchers in the field would sign, is that there is a plausible mechanism and it does not yet fit the numbers. That phrase is going to recur, because the nickel was only the beginning and the next result came from the coordinated fleet, and it was about the most basic property a comet has, what it is made of. Every comet in our solar system is, to a first approximation, dirty water ice. Water is the dominant volatile, usually by a large margin. Carbon dioxide is present but secondary. Carbon monoxide is present in smaller amounts still. That is the recipe tested across every comet we have ever measured, from Halley to Hale-Bopp to 67P/Churyumov-Gerasimenko, which the European Rosetta mission orbited for 2 years and studied in obsessive detail. Researchers combined spectral data from MAVEN at Mars, from the James Webb Space Telescope, and from SPHEREX, 3 instruments in 3 completely different places measuring 3 different wavelength regimes, and derived the production rates of water, carbon dioxide, and carbon monoxide for 3I/Atlas. The relative rates were unlike a normal comet. 3I/Atlas was releasing carbon dioxide in enormous quantity relative to water. Far more than any typical solar system comet. It was not a dirty snowball with some carbon dioxide mixed in. It was a body in which carbon dioxide played a leading role, and Webb's later observations confirmed and reinforced that finding rather than softening it. Why does that matter? Because the ratio of carbon dioxide to water in a comet is a thermometer that reads backward in time. It records the temperature of the place where the object formed. Carbon dioxide freezes at a much lower temperature than water. For a body to lock away that much carbon dioxide in its ice and hold it there, it must have condensed in a region substantially colder than the zone where our own comets were assembled. Farther from its star, or around a fainter star, or in a disk that was simply, fundamentally colder than the one that made us. The picture beginning to emerge was of an object built in a genuinely alien environment. Not alien in the sense of little green men. Alien in the far more profound sense that the physical conditions of its birthplace were different from ours in ways we can read directly in its chemistry, billions of years later, from 100 million miles away. And then it went behind the sun. For several weeks around the 29th of October 2025, 3I/Atlas was effectively invisible from Earth. It rounded the sun at a distance of about 130 million miles, closer to our star than Mars ever gets, and it did so while sitting in the glare that no ground-based telescope can penetrate. The Mars fleet had a better angle and kept working, but the finest instruments humanity possesses were shut out during the object's most violent, most revealing hours. The blackout ended in November, and when 3I/Atlas re-emerged into the morning sky, it had changed. The first surprise was brightness. The object came out considerably brighter than the standard models had predicted, and its coma had swelled dramatically. Solar heating had reached deeper into the body and something down there had woken up. The second surprise was structure, and it is here that the story acquires the details that would launch 1,000 arguments. Comets grow tails. That is what they are famous for. The mechanism is simple and it has been understood since the 1950s. The solar wind, a stream of charged particles blowing constantly outward from the sun, and the pressure of sunlight itself, push the gas and dust away from the nucleus, so the tail always points roughly away from the sun. It does not trail behind the comet like exhaust. It points outward, radially, regardless of which direction the comet is traveling. 3I/Atlas had grown a feature pointing the wrong way, toward the sun. Astronomers call this an anti-tail, and it is not, in itself, unheard of. There is a well-known geometric explanation. Large, heavy dust grains, too massive for radiation pressure to push around efficiently, get left behind along the comet's orbital path, and when Earth happens to cross the plane of that orbit, we see that trailing sheet of debris edge on as a spike that appears to point sunward. It is a perspective illusion. Comet Arndt-Rowland produced a famous one in 1957. The trouble is that the geometric explanation makes specific predictions about timing. The anti-tail should appear only when Earth is near the comet's orbital plane, and it should vanish when we move away. The sunward feature on 3I/Atlas was visible in the highest resolution Hubble imagery from July 2025, before perihelion, and it persisted through July and most of August, across a range of viewing geometries. Analysis of that imagery suggested it was not a diffuse sheet of dust seen edge-on but something narrower. A collimated structure, a jet, aimed toward the sun and extending roughly 10 times farther than the fan of material going the other way. And after perihelion, the imaging revealed more. Processing of some 40 Hubble images taken between November 2025 and February 2026, using a filter that mathematically removes the smooth symmetric glow around a nucleus in order to expose faint asymmetric structure, revealed a system of narrow mini-jets, symmetrically separated, emerging from the nucleus. Along with them, evidence of a long sunward-pointing feature stretching over 100,000 kilometers, and a wobble in the whole structure with a period of a few hours, consistent with a rotating nucleus whose jets sweep around like the beam of a lighthouse. Now, jets on comets are absolutely normal. Rosetta photographed them in stunning detail on 67P. A comet nucleus is not uniform. It has a crust, it has fractures, it has pockets of volatile ice buried at different depths, and when the sun heats it, gas escapes preferentially through weak points, producing collimated streams rather than a uniform fog. The wobble is normal too because the nucleus rotates, so the jets rotate with it. But the specific geometry reported here, jets with a narrow opening angle emerging near the rotational poles, arranged with a symmetry that persisted across months of observation, is unusual enough that it drove the next and most consequential piece of evidence. Because those jets were pushing. When gas erupts from one side of a comet, it acts as a rocket engine. Small, inefficient, but relentless. Over weeks and months, that thrust measurably alters the object's trajectory. Astronomers have measured this effect on comets for decades, and they have a standard mathematical framework for it. 3 parameters describing the push in the radial direction, away from the Sun in the transverse direction along the orbit, and in the normal direction perpendicular to the orbital plane. 3I/Atlas showed a clear non-gravitational acceleration around perihelion. That in itself was not surprising. It is a comet, it was outgassing, of course it got pushed. But when independent teams did detailed analyses of the orbital data, drawing on astrometry from more than 200 observatories around the world, some of them concluded that the push was not primarily radial. There were significant components in the transverse direction, meaning the object was being nudged along or against its direction of travel rather than simply shoved away from the Sun. A large non-radial acceleration is unusual, though not impossible. It is exactly what you would expect from localized jets emerging at odd angles from a rotating body, rather than uniform sublimation from the whole sunlit surface. The high-resolution imaging supports precisely that interpretation. Localized sources of mass loss.
Kollimated wobbling pole adjacent jets.
So the physics hangs together. Mostly, there is genuine disagreement in the published literature about the exact magnitude and direction of the acceleration, with different groups deriving somewhat different values from the same underlying data, which is the ordinary and healthy condition of science working on a hard problem in real time. But that small, measured push had a consequence that nobody anticipated, and it is the single strangest coincidence in the entire affair. Because of the non-gravitational acceleration, the projected trajectory of 3I/Atlas shifted slightly. And that shift changed where the object would pass Jupiter. Every planet has an invisible border. Physicists call it the Hill sphere, and the number that defines it is the Hill radius. Inside that border, the planet's gravity dominates. A small object placed there can orbit the planet stably, held in place, and the Sun cannot pull it away. Outside that border, the Sun wins, and anything you leave behind will be stripped and dragged into its own solar orbit. It is not a wall. It is a threshold. Every moon of every planet in the solar system orbits inside its planet's Hill sphere. That is not a coincidence. It is the definition of being a moon. For Jupiter, the largest planet, the Hill radius is enormous, and on the 16th of March 2026, with Jupiter at a distance of about 784 million kilometers from the Sun, that radius worked out to approximately 53.5 million kilometers. On that same date, 3I/Atlas made its closest approach to Jupiter. NASA's Jet Propulsion Laboratory computed the encounter distance using the full orbital solution, incorporating the observed non-gravitational acceleration, and the forecast came out at approximately 53.4 million kilometers, with an uncertainty of around 60,000. 53.4 against 53.5. The two numbers match within the measurement error. Out of all the possible distances at which an object crossing the outer solar system could pass Jupiter, from millions of kilometers closer to hundreds of millions farther away, 3I/Atlas threaded the encounter at the exact radius where Jupiter's gravitational authority ends and the Sun's begins. And it did so because of the tiny course change imparted by its own outgassing near perihelion. Avi Loeb, the Harvard astrophysicist who became internationally known for his willingness to take the artificial origin hypothesis seriously in the case of Oumuamua, assigned that coincidence a probability of roughly 4 in 100,000. And he pointed out something that makes the coincidence considerably more pointed. The Lagrange points L1 and L2 of the Jupiter-Sun system, the balance points where the gravitational tug of planet and star cancel out, sit essentially at the Hill radius. Those points are the single most efficient parking spots in the entire Jovian neighborhood. A satellite placed there requires almost no fuel to maintain its position. It is where any competent engineer would put a long-duration observation platform. Loeb's hypothesis, offered explicitly as a hypothesis and not a claim, was that if 3I/Atlas were an artificial object designed to deploy instruments into the Jupiter system, this is the trajectory it would fly. He did not stop there. Over the course of the encounter, he compiled a running list that eventually reached more than 20 separate anomalies, ranked by how improbable he considered each one. The nickel without iron. The sunward jet 10 times longer than the anti-sunward fan. The 3 symmetric mini-jets separated by 120 degrees. The size problem. The extreme age. The non-radial acceleration. And 2 more that are worth stating plainly because they get quoted constantly and they deserve to be understood properly. The first is that on the 22nd of January 2026, 3I/Atlas aligned with the Sun-Earth axis to within about 7/10 of a degree, and at that moment its sunward feature pointed directly at our planet. The second is that the direction 3I/Atlas arrived from lies within about 9 degrees of the patch of sky from which the WOW signal came in 1977, the still unexplained 72-second radio burst detected at Ohio State University that remains the most famous single-candidate signal in the history of the search for extraterrestrial intelligence. He put the odds of that alignment at roughly 6 in 1,000. Now, this is the moment in the story where a documentary has a choice to make, and I want to be direct with you about which choice we are making, because you deserve the actual state of the evidence rather than the version that is more fun to narrate. Those anomalies are real observations. The nickel measurement is real. The chemistry is real. The Hill radius coincidence is arithmetically correct and anyone can verify it. Loeb is not fabricating data, and the reflexive dismissal he receives in some quarters is not, in itself, a scientific argument. But there is a fundamental statistical trap here, and it has a name. Astronomers call it the look elsewhere effect. Statisticians call it multiple comparisons. In plain English, if you examine a complex natural object with modern instruments and you generate hundreds of independent measurements, and then you go hunting for numerical coincidences among them and among every other number in the solar system, you will find some. Not might, will. It is a mathematical certainty. The probability that any specific coincidence occurs may be 1 in 10,000, but the probability that some coincidence occurs somewhere in a dataset of that size approaches 1. The WOW signal alignment is the clearest illustration. 9 degrees is not a small target. A 9-degree radius circle covers roughly 0.6% of the sky, which sounds tiny until you ask the right question. The right question is not, what are the odds it came from there? The right question is, how many notable directions are there in the sky that would have prompted somebody to write an article if the object had come from one of them? The galactic center. The WOW signal. Any of a dozen famous nearby stars. Any of the SETI candidate fields. Once you count all the targets that would have counted as a hit, a 9-degree match stops being remarkable. The same logic applies, more weakly but still meaningfully, to the Hill radius. The Peryhove distance and the Hill radius are not arbitrary independent numbers pulled from a hat. Both depend on Jupiter's distance from the Sun. And an object on a hyperbolic path crossing the outer solar system has to pass Jupiter somewhere, and the range of plausible distances is not infinite. None of which proves the coincidences are meaningless. It means they are not, by themselves, evidence of design. And so the field did the only thing the field could honestly do. It went and looked. Not metaphorically, literally. If 3I/Atlas were a technological object, the most direct test available to us is to listen for radio emission, because every piece of technology humans have ever sent into space leaks radio, and a probe operating in another star system's neighborhood would have very little reason to be silent. The first serious attempt came in December 2025, using some of the most sensitive radio instrumentation on the planet. The result? No technosignature. The observations set limits so tight that they excluded any isotropic continuous wave transmitter above about 1/10 of a watt. 1/10 of a watt. That is less power than a cell phone uses. Less than a Christmas tree bulb. If 3I/Atlas were broadcasting in any direction at all in the frequency ranges searched, at a power level a hobbyist could achieve with hardware from an electronics store, we would have detected it. Then, in the spring of 2026, the SETI Institute mounted a longer campaign using the Allen Telescope Array at the Hat Creek Radio Observatory in Northern California, a purpose-built facility designed from the ground up for exactly this task. 7 hours of observation, scanning a wide range of radio frequencies, hunting for anything that looked artificial. They found candidate signals. They always do. and every single one traced back to technology on the surface of the Earth or to our own satellites in orbit. Human noise, our own reflection. The paper was published in the Astronomical Journal in June 2026, and its conclusion was unambiguous.
Notech signatures.
The most sensitive search ever conducted on an interstellar object, and the answer came back empty. That is not a disappointing result. I want to be clear about that because there is a tendency to treat a null result as a failure, and it is the opposite. A null result is a boundary. It is a fence posted in the dark. We now know, with quantitative precision, something we did not know before about what 3I/Atlas is not. That is exactly how science is supposed to work, and it is the reason the search was worth conducting even though almost everyone involved expected the outcome. And there is something quietly admirable in the fact that it happened at all. A hypothesis was raised. It was unpopular. Rather than mock it, a serious institution pointed serious hardware at the sky and tested it, and reported the result honestly. So where does that leave us? It leaves us with an object that is not sending radio signals, that behaves in most respects like a comet, that has a coma and a tail and jets and outgassing and non-gravitational acceleration exactly as a comet should, and that is simultaneously wrong in its chemistry, wrong in its metal ratios, wrong in its age, wrong in its origin, and wrong in ways that no amount of careful modeling has yet fully repaired. The consensus among researchers is that 3I/Atlas is a comet. It is a comet from somewhere else, formed under conditions we have never sampled, and its oddities reflect an alien formation environment rather than an alien engineer. But that consensus was formed before the summer of 2026. And in the summer of 2026, the James Webb Space Telescope finished processing a dataset it had collected on the object's way out, and NASA published what it found, and the word that appeared in headline after headline was one that scientists deploy carefully. Mysterious. On the 1st of June 2026, NASA announced that the James Webb Space Telescope had detected methane on Comet 3I/Atlas. That sentence does not sound like a bombshell. Methane is not exotic. It is the simplest hydrocarbon there is, one carbon atom holding 4 hydrogens, the main component of natural gas, the stuff that heats American homes and cooks American dinners. It is everywhere in the cosmos. There is methane on Titan, in lakes. There is methane in the atmospheres of Uranus and Neptune, giving them their color. There is methane in interstellar clouds. So why did this particular detection stop the field in its tracks? 3 reasons, and each one is a separate blow. The first is that it had never been done. Methane had never been directly detected on an interstellar object. Not on Oumuamua, which showed no volatile emission at all. Not on Borisov, despite intensive study. This was the first time in history that anyone had measured methane in material that formed around another star and then traveled here as a solid body. A first in the plainest sense of the word. The second reason is the amount. The team, led by Caltech astronomer Matthew Belyakoff and colleagues, used the mid-infrared instrument aboard Webb to take the first mid-infrared chemical fingerprint ever obtained of an interstellar object, observing on 2 separate dates in December 2025 as 3I/Atlas traveled back out of the solar system after rounding the sun. The results were published in the Astrophysical Journal Letters in April 2026 and announced publicly that June. And the quantity of methane relative to water was surprisingly high. High enough that the researchers noted there were few good analogs anywhere in our own solar system. Not a trace. Not a marginal detection at the edge of the noise. A lot of methane in a proportion our own comets essentially do not exhibit. The third reason is the one that turns a chemistry result into a genuine mystery, and it is a matter of timing. The methane was not there on the way in. On the inbound leg, as 3I/Atlas fell toward the sun and astronomers scrutinized it with everything they had, methane was not detected. Then the object rounded the sun, endured the hottest hours of its transit, emerged on the far side, and on the way out, methane appeared in abundance. That does not happen with a normal comet. In a normal comet, the volatiles come off in order of how easily they sublimate, and methane is one of the most volatile substances a comet can contain. It turns to gas at extraordinarily low temperatures, far colder than water ice requires. If a comet has surface methane, that methane escapes early, at great distances from the sun, long before water ever begins to flow. Methane is the first thing to go, not the last. For methane to appear only after perihelion, only after maximum heating, there is essentially one explanation the researchers could construct, and it is a startling one. The methane was buried, not on the surface, not in the outer crust, down in the subsurface, beneath a protective layer of ice, insulated and sealed away, where it survived without escaping. And it stayed sealed until the heat of the closest solar approach penetrated deep enough into the body to reach it, at which point the frozen methane sublimated and forced its way out. Consider what that implies about the object's history. Methane is so volatile that it cannot survive on an exposed surface anywhere close to a star. For 3I/Atlas to have carried a reservoir of it across the galaxy for billions of years, that reservoir had to be shielded, and it had to remain shielded through the entire journey. Which means the object has not passed close to a star in all that time. Not once. If it had, the heating would have driven the methane out long ago, and there would have been nothing left for Webb to detect. Which in turn means the pass through our solar system in 2025 may have been the first time this object has come near a star since the day it was ejected from the disk that made it. The first time in something between 3 and 11 billion years. We were not merely observing an ancient object. We were observing an ancient object being opened. The sun cracked a seal that had held since before the Earth existed, and released a puff of gas that had been locked in the dark for a span of time longer than the history of complex life on this planet, and a telescope 1,000,000 miles from Earth caught it. Webb's observations confirmed and sharpened the rest of the picture too. The extreme carbon dioxide enrichment held up. 3I/Atlas releases far more carbon dioxide relative to water than typical solar system comets, and that finding is now nailed down by mid-infrared spectroscopy rather than inferred. Webb also watched the gas production decline sharply as the object receded from the sun, with water dropping most dramatically of all, which is exactly what should happen as a body crosses back outside the snow line and its water ice refreezes. That, at least, was textbook behavior. Reassuringly ordinary physics operating on a thoroughly extraordinary object. And the molecular inventory kept growing as other instruments reported in. Ground-based spectroscopy at visible wavelengths added gas-phase cyanogen along with the atomic nickel. Radio observations with ALMA, the array of dishes on the Chichinanter Plateau in Chile, added methanol and hydrogen cyanide. Cyanogen, methanol, hydrogen cyanide, carbon dioxide, carbon monoxide, methane, formaldehyde, water. Pause on that list because there is something in it that is easy to miss if you are only counting anomalies. Hydrogen cyanide and formaldehyde are not merely interesting molecules. They are the raw feedstock of prebiotic chemistry. Give hydrogen cyanide the right conditions, liquid water and mineral surfaces and energy, and it polymerizes into the nucleobases, the letters of the genetic alphabet. Formaldehyde, under similar conditions, produces sugars, including ribose. These are the ingredients from which, on one particular world, 4 billion years ago, something began to copy itself. We have found them before on our own comets. Rosetta detected an extraordinary chemical zoo on 67P, including glycine, the simplest amino acid. That discovery underpins one of the most compelling ideas in origin of life research, that the young Earth was seeded with organic complexity by comet and asteroid impacts, that the ingredients of biology were delivered rather than manufactured locally. But every comet we have ever measured was made from the same original material as the Earth itself. The delivery argument has always had a circularity problem lurking inside it. Of course, the comets have the same organic chemistry as the Earth. They are made of the same stuff. 3I/Atlas is not made of the same stuff. It was assembled around a different star, from a different cloud, in a different epoch of galactic history, under measurably different physical conditions. And it is carrying the same prebiotic molecules. That is a data point of a fundamentally different kind. It is one object, and one object is not statistics, and no responsible scientist would build a conclusion on it. But it is a first sample, and what the first sample says is that the chemical machinery that leads toward life may not be a local accident. It may be a common feature of how planetary systems assemble themselves, anywhere, at any point in the history of the universe. And then, in July 2026, came the result that closed the case on the object's origins and simultaneously deepened everything about it. Isotopes. Here is the concept, and it is the most powerful dating tool in astrophysics, so it is worth taking slowly. Every chemical element comes in variants called isotopes, identical in their chemistry but differing in the number of neutrons in the nucleus. Carbon has 2 stable ones. Carbon-12, with 6 protons and 6 neutrons, is the common form, the backbone of organic chemistry. Carbon-13 has 1 extra neutron. It behaves almost identically, but it is made differently. Carbon-12 is produced abundantly in the cores of massive stars and released when they explode. Carbon-13 is produced predominantly later in cosmic history, in the interiors of red giants, stars in the late stages of their lives, through a different nuclear pathway. Which means the ratio between the two has been changing steadily throughout the history of the galaxy. Early on, carbon-12 dominated overwhelmingly. As generation after generation of stars lived and died, carbon-13 accumulated. The carbon isotope ratio is a clock. Read it, and you read the epoch in which the material formed. 2 independent efforts read it on 3I/Atlas. Webb's near-infrared spectrograph measured carbon isotopes in the compounds pouring off the comet, carbon monoxide, carbon dioxide, and organic molecules including methanol, formaldehyde, and methane, and it found that 3I/Atlas contains far more carbon-12 relative to carbon-13 than anything measured in our solar system. More than in nearby planet-forming disks around other stars. More than in local molecular clouds. More than in the interstellar medium around us. Then a team led by Cyrielle Oppidum of the University of Edinburgh, co-led by Jean Manfroid and Damien Hutsmekers of the University of Liège in Belgium, used the ultraviolet and visual Echelle spectrograph on the Very Large Telescope to measure both carbon and nitrogen isotope ratios in cyanide molecules in the coma. These were the first measurements of their kind ever made on a comet formed outside our solar system. The results were published in Nature Astronomy in July 2026. The 2 independent methods agreed. High carbon-12 to carbon-13. Unusual nitrogen isotope ratios. A chemical signature that does not match our solar system, does not match the local interstellar medium, and does not match the young planet-forming disks astronomers can observe around nearby stars. The interpretation is direct, and it is almost impossible to escape. This material condensed at a time when the galaxy had not yet accumulated its later burden of heavy isotopes. Formed early, and the team's analysis pointed specifically to an origin in the outer regions of an old star system, far from its parent star, which fits perfectly with the carbon dioxide enrichment and the buried methane and the extreme cold that all of it implies. Evidence from multiple independent teams, using different instruments, measuring different molecules, converged on the same conclusion. 3I/Atlas is more than twice as old as the Sun. Some analyses push further. Combining the kinematic age constraints with the isotopic evidence, certain estimates place the object's formation as far back as 10 to 12 billion years, which would make it very nearly as old as the Milky Way itself. If those numbers hold, then 3I/Atlas condensed in a galaxy that would be unrecognizable to us. A galaxy still assembling, still merging with smaller companions, blazing with star formation, thick with the debris of a violent youth. And the star it formed around is almost certainly gone. A star massive enough and bright enough to have a substantial planet-forming disk 12 billion years ago has long since burned through its fuel. It swelled into a red giant, shed its outer layers into a glowing planetary nebula, and collapsed into a white dwarf, which has been cooling ever since. Or, if it was more massive, it exploded, and the explosion is what tore this object free and hurled it into the dark. Which means 3I/Atlas may be a relic of a solar system that no longer exists. Not a distant one, a dead one, a planetary system that formed and evolved and possibly hosted worlds and possibly hosted oceans and then died, and every trace of it has been erased from the galaxy except for this one fragment of ice and dust, still moving, still carrying its original chemistry unchanged, still holding methane that was frozen before the Earth was a cloud. We got to read it. For 13 months, we got to read it. And now we are losing it. The departure is the part of the story nobody writes headlines about, and it is the part that carries the most weight. Right now, as you watch this, 3I/Atlas is somewhere past the orbit of Jupiter, heading outward and away, moving at a speed that no human vehicle has ever come close to matching. It is getting fainter every night. The coma is collapsing as solar heating fades. The water has already refrozen. The methane that Webb caught, the ancient gas that had been sealed for billions of years, has stopped venting and will not vent again. Whatever is left of that reservoir is going back into deep freeze, and it will stay frozen for as long as the object exists. Observations at the Very Large Telescope, which produced some of the most important results in this entire investigation, are nearing their end simply because the object is becoming too dim to work with. Instrument by instrument, the observation campaign is shutting down. Not because anyone chose to stop, because there is nothing left to see. And it is never coming back. That is not a figure of speech, and it is not a dramatic flourish. The orbit is hyperbolic with an eccentricity above 6, and hyperbolic means open, and open means it will leave the sun's gravitational influence entirely and continue in a straight line through interstellar space forever, or until it encounters another star, which on average will take hundreds of millions of years and may never happen at all. In 10,000 years, it will be far beyond the Oort cloud. In 1,000,000 years, it will have crossed a meaningful fraction of the distance to the nearest stars. In 100 million years, it will be somewhere on the other side of the galaxy, and the constellations we know will have dissolved, and the sun will have completed a lap around the galactic center, and 3I/Atlas will still be moving at the same 58 kilometers per second, carrying its methane and its cyanide and its strange nickel and its ancient carbon unchanged, indifferent, alone. Everything we know about it, we know now. There will be no follow-up mission. There will be no second look. Whatever we failed to measure between July 2025 and the summer of 2026 is lost to the human species permanently. Which is precisely why NASA did something that deserves more attention than it gets. Every observation from every one of those missions, from Hubble and Webb and SPHEREX and TESS and MAVEN and Lucy and Juno and the rest, is being placed in public archives. Open, free, available to anyone with an internet connection and the curiosity to look. The reasoning behind that decision is not sentimental. It is strategic, and the strategy has already paid off. The TESS prediscovery detection, the one that revealed 3I/Atlas may have been active far beyond the snowline, came out of archival data that had been sitting untouched for over a year, collected by a mission that was not looking for comets, analyzed by researchers who were not part of the original campaign. The comparison of water and carbon dioxide and carbon monoxide production rates, one of the foundational results of the whole affair, came from combining data across 3 separate missions that were never designed to work together. NASA's chief science data officer described the agency's archives as a gold mine of discoveries waiting to be made. And in this case, that is not public relations language. It is a literal description of what happened. The most important findings about 3I/Atlas emerged not from single instruments but from combinations, and combinations require that the data be accessible to people who were not in the room when it was collected. So the object is gone and the dataset is permanent, and somewhere out there is a graduate student who has not yet chosen a thesis topic who will find something in that archive in 2035 that nobody noticed in 2026. That is the honest hope. It is also the only one left. But there is a much larger reason not to be discouraged, and it changes the whole shape of this story from an ending into a beginning. 3 interstellar objects in 8 years is not a natural rate. It is an artifact of our equipment. Interstellar objects have been passing through our solar system continuously for 4.5 billion years. Estimates suggest that at any given moment there may be thousands of them inside the orbit of Neptune. They have always been here. We simply could not see them. They are small, they are dark, they move fast, and until very recently our sky surveys were not sensitive enough or fast enough to catch a faint mover before it was gone. Oumuamua was found in 2017 by Pan-STARRS in Hawaii, a survey that had only recently reached full capability. Borisov was found in 2019 by an amateur astronomer in Crimea using a telescope he built himself, which tells you something about how marginal these detections were. 3I/Atlas was found by a survey network that did not exist a decade earlier. And now something has come online that changes the equation entirely. On a mountain in northern Chile, not far from the telescope that found 3I/Atlas, sits the Vera C. Rubin Observatory. It houses an 8.4-meter mirror and the largest digital camera ever constructed for astronomy, a 3.2 gigapixel instrument the size of a small car. Its mission, the legacy survey of space and time, is to photograph the entire visible southern sky every few nights, continuously, for 10 years, producing a time-lapse movie of the universe at a level of detail no previous instrument could approach. Rubin will detect faint moving objects at a rate that will make the current era look like the age of the naked eye. Projections for how many interstellar visitors it should find vary depending on assumptions, but the estimates run from several per year into the dozens. Which means the situation we are in right now, this frustrating, precious, once-ever situation in which we squeeze every drop of information out of a single object because we may never see another, is about to end. We are going to get a population. And a population is where science really begins, because a population lets you ask questions that a single object cannot answer. Is the extreme carbon dioxide enrichment of 3I/Atlas typical of ancient objects? Or is it a peculiarity of one body? Do thick-disk interstellar objects systematically differ from thin-disk ones in ways we can measure? Is buried methane common? Is the strange nickel signature a universal feature of interstellar comet chemistry that we have simply never had enough samples to notice? Do the prebiotic molecules show up every time in every object from every era, which would be one of the most consequential findings in the history of biology? We are perhaps a decade away from being able to answer those questions with real statistics, not speculation, numbers, and there is more than observation on the table. Several space agencies have studied the concept of an interstellar object interceptor, a spacecraft parked in a parking orbit, fully fueled and waiting, ready to launch the moment a suitable target is identified. The European Space Agency has an approved mission of exactly this type in development, designed to wait in space for a target and then chase it down. The engineering is brutally difficult because these objects arrive fast and are identified late, but it is not impossible. And the payoff would be extraordinary. Not a spectrum from 100 million miles away, but a close approach. Images of a surface, possibly a sample. Somewhere in the next 20 years, a human-built machine may fly alongside a piece of another solar system and photograph it. That is a genuinely reasonable expectation, not a fantasy. Which brings us back to the object that started it all, and to the question that has hung over this entire investigation from the beginning. What is the honest answer? What is 3I/Atlas? The consensus, and it is a real consensus held by the overwhelming majority of working astronomers, is that it is a comet. An interstellar comet, formed in the outer reaches of a very old, very cold planetary system, ejected into the void billions of years ago, preserved unchanged by the deep cold, and briefly warmed by our star before continuing on its way. Every behavior it exhibited is a cometary behavior. It grew a coma. It grew a tail. It vented gas through jets. It was pushed off course by that venting. It faded as it receded. It emitted no radio signals when the most sensitive instruments on Earth listened for 7 hours. Its chemistry is unusual, but unusual is exactly what you should expect from an object that formed somewhere else. The anomalies are, in most cases, either explained or explicable in principle. The nickel has a plausible organometallic pathway even if the ratio is not yet fully reproduced. The anti-tail and jets are consistent with a rotating nucleus venting through localized weak points. The non-radial acceleration follows from the jet geometry. The Hill radius coincidence is a coincidence, and coincidences are what you get when you generate thousands of numbers. That is the sober assessment, and it is almost certainly correct. But I want to end with something more careful than a verdict, because there is a real question buried underneath the noise and it deserves to be stated cleanly. The mainstream position is not that 3I/Atlas is fully understood. That is the version that gets flattened into a headline, and it is wrong. Read the actual papers and the language is far more cautious. Researchers describe findings with few analogs in the solar system. They describe ratios that current models do not reproduce. They describe an object that combines cometary behavior with properties that are, in the technical literature, repeatedly called unprecedented. Both things are true at once, and holding both at once is the hard part. It is a comet, and we do not fully understand it. That is not a contradiction. That is the actual condition of the science, and it is a far more interesting place to stand than either of the two comfortable positions on either side of it. So let us gather what we actually know, and let us be precise about it, because precision is the only thing that separates wonder from noise. We know that on the 1st of July 2025, a NASA-funded survey telescope in Chile recorded a moving point of light, and that within days the orbital solution came back with an eccentricity above 6, which is a number that cannot be produced by anything born in our solar system. It is only the third such object ever confirmed out of 5,000 years of watching. We know it was traveling at roughly 58 kilometers per second before the sun ever touched it, that it accelerated to about 153,000 miles per hour at closest approach, and that it left carrying exactly the speed it arrived with. Our entire star system failed to slow it down by a measurable amount. We know that it never came anywhere near Earth. The closest it got was about 170 million miles, nearly twice the distance from here to the sun. There was never a threat. There was never a scenario in which there was a threat. That deserves saying plainly because a great deal of nonsense circulated about this object, and none of it was ever supported by the orbital mechanics, which were public, precise, and unambiguous from the first week. We know its nucleus is somewhere between about 1,400 feet and 3.5 miles across, and that the upper end of that range sits uncomfortably with our estimates of how much large material planetary systems eject. We know it was already active out around 6 astronomical units, far beyond the distance where water ice can sublimate, which told us from the very beginning that something other than water was driving it. We know it is releasing carbon dioxide in a proportion to water that no typical solar system comet approaches, which encodes a formation environment substantially colder than the one that built our own comets. We know its coma contained atomic nickel vapor at distances where metals cannot boil, with strikingly little iron beside it, a ratio that current chemistry does not cleanly reproduce. We know that the James Webb Space Telescope collected the first mid-infrared chemical fingerprint of an interstellar object ever obtained, and that it found methane, for the first time in history on a visitor from another star, in surprisingly large amounts relative to water, and that the methane appeared only on the way out, which means it was buried, and which means this object had almost certainly not passed close to a star at any point in the billions of years it spent crossing the galaxy. We know its molecular inventory includes hydrogen cyanide and formaldehyde and methanol, the raw material from which nucleobases and sugars are built, and that this is the first time those molecules have been confirmed in a body that formed around a different star. We know from 2 independent measurements, one by Webb and one by the Very Large Telescope, that its carbon isotope ratio is unlike anything in our solar system, unlike the local interstellar medium and unlike nearby planet-forming disks, and that this points to formation in an era before the galaxy had time to build up its later isotopes. We know its motion places it in the thick disk of the Milky Way, the ancient stirred-up layer of stars that formed while the galaxy was still assembling. And we know that every line of evidence, from kinematics to isotopes to chemistry, converges on the same extraordinary conclusion. This object is at minimum twice the age of the Sun, and quite possibly close to the age of the galaxy itself. We know that the SETI Institute pointed the Allen telescope array at it for 7 hours and found nothing, that earlier campaigns ruled out any transmitter above 1/10 of a watt, and that every candidate signal traced back to our own machines. And we know that more than a dozen NASA missions, from Earth orbit to Mars to the asteroid belt to Jupiter, interrupted their own science to look at it because they understood that the opportunity would not repeat. That is what we know. And now here is what I think it means, which is a separate thing, and I want to keep the two clearly apart. For the entire history of our species, we have studied exactly one planetary system from the inside. One. Every rock we have ever cracked open, every meteorite that has ever fallen into a museum drawer, every sample returned by every mission from the Moon and from Bennu and from Ryugu and from the tail of Comet Wild 2, every last atom of it condensed out of the same collapsing cloud 4.5 billion years ago. We have been studying our own family, exhaustively, and mistaking it for the universe. We have inferred the rest, brilliantly, rigorously, and entirely at a distance. We have read the atmospheres of planets around other stars by watching starlight dim. We have weighed alien worlds by the wobble they impose on their suns. It is magnificent work, and it is all indirect. And then a piece of somewhere else fell through our neighborhood at 150,000 miles an hour, and for 13 months we got to look at it. Not infer. Look. And the first thing we learned, the very first lesson, was that our sample of one was misleading us. The chemistry is different. The isotopes are different. The temperature of formation was different. The proportions of the most basic molecules in the most basic kind of body are different. Everything we thought we knew about how planetary systems assemble themselves was built on a single example, and the moment we saw a second, it did not match. That should not depress you. That should thrill you. It means the universe is more varied than our models, which is the single most reliable pattern in the history of science, and it is the reason there is any point in continuing to look. And the second lesson runs the other way, and it is the one I find harder to stop thinking about. The prebiotic molecules were there, formed around a different star in a different epoch out of gas with a different isotopic composition, under conditions colder than anything in our system, in a galaxy that had barely begun. And the hydrogen cyanide was there. The formaldehyde was there. The methanol was there. The carbon chemistry that leads, given water and time and a stable surface, towards self-replication. One sample proves nothing. I said that before and it remains true. But if it turns out, when Rubin Observatory starts delivering these objects by the dozen, that this is the normal pattern, that the ingredients of life are simply what happens when gas and dust condense around any star anywhere at any point in the last 12 billion years, then the question that has haunted us since we first understood what stars were changes character entirely. It stops being a question about chemistry. The chemistry would be settled. It would become a question about what happens next and how often, and whether the step from chemistry to biology is a routine one or a miracle. We do not know. But for the first time, we have a way to find out that does not depend on guessing. And here is the last thing. 3I/Atlas is still out there. Right now. It has crossed the orbit of Jupiter and it is climbing away from the sun, dimming, cooling, its brief thaw ending. In a few years, it will be beyond the reach of any telescope we possess. It will continue outward through the Kuiper belt, through the Oort cloud, out past the last thin wisp of our star's influence, and into the true dark between the stars, where it has spent almost the entirety of its existence and where it will spend all the rest. It will not stop. There is nothing out there to stop it. Long after the last human telescope has been dismantled, long after the sun has swollen into a red giant and swallowed the inner planets and collapsed into a cinder, long after the constellations have scattered and reformed 100 times over, that object will still be moving, still carrying its ancient carbon, still holding, sealed beneath a crust of ice, whatever methane the sun failed to reach. And for 13 months, on one small wet planet orbiting an unremarkable star, a species that has existed for a rounding error of its lifetime pointed everything it had at it and worked out where it came from. We figured out that it was older than our sun. We measured the temperature of the cloud that made it. We read the isotopes and dated it to a time before the Earth existed. We caught the moment its ancient methane escaped for the first time in billions of years, and we identified the gas from 100 million miles away using a telescope we launched into the cold ourselves. That is not a small thing. That may be the least small thing our species has ever done. The universe sent us a message that was not addressed to anyone. A piece of a dead star system, tumbling through the void with no purpose and no destination, carrying in its ice a record of conditions that existed before our planet was born, passed through once. It will never pass again. And we read it. That is what happened here. Not a threat, not a spacecraft, something rarer and, I would argue, far more remarkable. Proof that a mind that evolved on a savanna, in a body that lives less than a century, can look at a smudge of light moving against the stars and reconstruct the history of a world that died before the Earth was formed. 3I/Atlas is leaving. The window is closing. And somewhere out beyond Neptune, right now, the next one is already on its way in. We just have not seen it yet.